Welcome back. In this video lecture, we will discuss about expressions for capacitors, for parallel plate capacitor, spherical capacitor, and cylindrical capacitor. We will see how we can develop expressions of capacitance. As we have already discussed Laplace and Poisson's equations, and apart from that, we have seen what is actually a capacitance. Also, we have seen the SLT 18, right? So I hope that in this video lecture, after discussion of these different types of capacitors, I hope that you will be able to develop expressions for capacitors for different configurations, basic configurations. Now I'll start with the capacitor, which we have already discussed, right? Capacitor is an electric device composed of two conductors separated by a dielectric medium. And the capacitance which is stored in this one is given by the charge which is present, equal and opposite charge present on either side of the plates, and the potential difference between them, isn't it? And it depends upon the charge and also on the dielectric medium and also on the potential, isn't it? So now we'll start with the basic configuration of parallel plate capacitor. Shown on the figure is a parallel plate capacitor. See, which means that this is one idea, right? Plate 1 and this is plate 2. This representation is shown here. So this is plate 1, the bottom is a plate 1. So this is plate 1, and on the bottom side you do have plate 2, and each plate has a cross-section area of A, and the separation between the plates is given by T, which is nothing but a thickness or separation between the plates. And these two plates are provided. See, this is the fashion. Okay, this can be across any voltage source. So this voltage source develops automatically charges, right, to flow through it. So the following figure shows a typical parallel plate capacitor. It consists of two flat parallel plates, each with a surface area and separated by a distance t. Let the medium which is separating these two is a dielectric medium, and it is having a permittivity of epsilon. You know that epsilon is equal to permittivity of free space into relative permittivity. So this is the basic assumption which I am taking before moving on to deriving the capacitance of this configuration. So two plates, each one with a cross-sectional area of A, is separated by thickness T and separated by a medium with permittivity epsilon. Now, let the capacitor is being charged by connecting those two terminals A and B. As you see, this is having a terminal A and this bottom is having a B, as shown here. So this A and B terminals, they are connected to a voltage source. So you will be having a voltage across these plates, and this voltage source, it develops charges across these plates uniformly. So let us suppose the surfaces of the plates, they do have this uniform charge density. See, right? Right, this plate, okay, now charges are being deposited on this one uniformly, because you are here also on the bottom surface also, let us suppose, and this charge density is given by sigma coulombs per meter square, because this is an area, right? So I am taking surface charge density. Now if I assume that the dimensions are known, if it is a known configuration, so what is the charge which is accumulated now? Surface charge density into area. This is a standard, assuming that it is a rectangle or a square. So assuming that it is a constant one, a known configuration. So the charge is nothing but surface charge density into area, which area you are considering, right? So this is the charge which is there on each of these plates. If this is the charge, you know what is electric flux which is coming out of the surface? You know electric flux is always equal to the amount of charge, right? If electric flux is a charge which is equal to sigma A, Now, you know electric flux density, which is equal to right. So, what is the surface area here? What is the flux here? The flux is Q and the surface area is A, which is again equal to surface charge density. So, your flux density is again surface charge density. Right. Now, you know that this is equal to epsilon E. So, what is E now? This is electric field intensity. Once you know electric field intensity, what I can calculate? Potential, right? V is equal to minus integral ED, right? So, in this case, I don't have any other, because everything is very simple configuration. So, I will directly take ED. I can take minus symbol, but I am neglecting here. So, what is E? So, this is my potential equation. V is equal to sigma epsilon T. Now, I do already have Q. What is Q? Epsilon A. Now, I do have potential. Now, what is the capacitance now? C is equal to Q by A, which is epsilon A. This is epsilon by, sigma A. This is sigma by epsilon into T. So, this is my expression. Capacitance of a parallel plate capacitor where configuration is known. Let us suppose if I don't know the configuration, I know only the charge density. In that case, what I will be doing? See, my charge density is this one. So, I may not be able to determine what is the charge of this one. So, what I will do? For the entire surface, right? So, automatically, what is my D here? My D also will be so I will get again epsilon, right? But whereas my E will be this one, so D will be minus integral ED. So minus epsilon by dot. Yeah, this is my V. So I may get these type of integration equations if I don't know the perfect dimensions of my area which I'll be considering. So C is my charge. If I don't know it, then automatically what I'll be getting? Here also I'll be getting this one. And here what I'll be getting? Minus. This is my expression for capacitance. Okay. So this is regarding the parallel plate capacitor. Now we will move on to spherical capacitor. In the spherical capacitor, we will assume that there is a normal capacitor. It is just like a point charge, right? So assuming that it is having a charge, and there is another sphere which is at infinity radius. We will leave that one. Assume that this particular one is having a radius of r. So normally, what is the voltage at any point due to this one? It is given by V is equal to Q by 4 pi epsilon r, right? So what is C here? C is equal to Q by V. This is Q by 4 pi epsilon r, which is equal to 4 pi epsilon r. So C is equal to 4 pi epsilon r. This is the capacitance of this particular isolated sphere when the other sphere is at infinity radius. Now let us suppose there are two spheres in this fashion. Two spheres. The inner one is having a radius of A, the outer one is having a radius of B, and R is one term which varies between A and B. So in this case, what is the capacitance of this particular configuration? So assuming that this separation between these two spheres is filled with a dielectric medium of epsilon. Now let the charge of Q is distributed uniformly on the outer shell. So this configuration, whatever I am taking, this is a dielectric medium, and the outer part is having a charge of plus Q. I'll take it as an uniform charge, and the inner part is having a uniform charge of minus q. So in this case, what is the electric field at any point in the center of this particular region? If I consider any of this particular region, which is of R, we have already calculated for this one. It is q by 4 pi epsilon r square. A is less than or right. If you don't remember that, we have done all these problems, right? If it is inside this one, it will be different. If it is on the surface of the inner sphere, it will be q by 4 pi epsilon a square. If it is in between, it will be q by 4 pi epsilon r square. If it is on this one, it will be 0, because the summation of these two charges is again 0, because we need to calculate what is the total charge here. So, but right now, as of now, assuming that I am considering only this particular area between A to B, this is the electric field. Now, what is V now? It is minus integral E dot ER. My distance is varying from A to B, so it was q by 4 pi epsilon r square dr. So q by 4 pi epsilon is constant, 1 by r square, the integration is 1 by r. If I substitute here, what I will be getting? Minus q by 4 pi epsilon 1 by r square dr, where r is equal to A to B. So I will be getting 1 by r, right? So it is q by 4 pi epsilon 1 by A to 1 by R. This is my expression for voltage voltage between these two spheres. Now I do already have Q and I do have V now. So what is the capacitance? Capacitance is equal to Q by V, which is Q by 4 pi epsilon, what I have got? 1 by A minus 1 by V, right? So this I can write it as, I'll check LCM here. This is AB, this is B minus A, right? So Q get cancelled, what I will be getting? I will be getting 4 pi epsilon AB by B minus A. This is my capacitance of concentric spherical shells. Done. So the next configuration is cylindrical capacitors. So this is the cylindrical capacitor. This is just like our conductor lines, a cable. Coaxial cylinders, where inner there is a cylinder of radius A, outer also we do have B, and they are extending or infinite length. So when they are extending over infinite length, I can't find out what is the area. So what I will be doing is nothing but I will be considering line charge density of lambda coulombs per meter. If you know the length, it will be lambda L. If you don't know the length, it will be just lambda coulombs per meter. So for this line charge densities, and assuming that the two cylinders are concentric, coaxial, we will try to determine. You know that the potential between these two, we have already tried to find out. You know the value of E, right? We have already done this particular problem. It was lambda by 4 pi epsilon r. This was E. So what was V? We have already done that one. It was lambda by 4 pi epsilon integral 1 by r dr, because V is equal to minus E dot dr, right? So r was varying from A to B. So for 1 by r, what we use it to get? The integral is log, right? So our expression was ln b minus ln a, which was ln b by a. This was the expression, right? So I am trying to utilize that expression, voltage across the cylinders. V is equal to lambda by, I think, yeah, it was 2 pi epsilon, right? We have already done this one. Yeah. So this is the voltage across the two cylinders. And you know that since charge is not directly available, what I will be doing is nothing but, if the charge, if I want, I am supposed to integrate it over the defined length, but here length has not been given, right? So what I will do is nothing but, if you want to determine capacitance for this one, what I am supposed to do, C is nothing but Q by V, which is nothing but, I don't know this particular term, but whereas this term I know now, lambda 2 pi epsilon ln b by a. This is capacitance. So capacitance per unit length. If it is per unit length, then this will become lambda into 1. So I'll take only lambda. Lambda by 2 pi epsilon naught ln d by a. This is it. So lambda will get cancelled. So what I'll get? 2 pi epsilon by ln d by a. This is capacitance per unit length of a coaxial cylinder. Right. So I hope now you have understood how to determine this capacitances for different types of charge configurations, different types of configurations. So this is your homework for you. You are supposed to determine the capacitance of coaxial cylinders per kilometer length in microfarads. Thank you.